Welcome to homework.
So we're shown the block that's basically connected through some cables that have stiffness values. So there's one cable here that's supporting a pulley, and another cable wrapped around the pulley supporting this weight. We're told that this spring has a stiffness 2K and this spring has a stiffness K. And so we want to figure, we're asked what the natural frequency of this system is. Now, the best way to do this, again, we can use a lot of kind of hand waving and shortcuts, but I think it's just best to write it out and draw free body diagrams of each of these components. So this spring has a tension T1 acting through it, and its top part here has a displacement x1. So that moves x1, and the x1 and t1 will be related by the spring constant. Now, if we look at the pulley, we're told that we can neglect the mass, so that we have t1 coming down here, and also the tension. The tension is in this cable that wraps around it is the same as it wraps around it, and so we get t1 here and t1 here, and t2 supporting the pulley here, and so that means that t2 has to be twice t1. Now, if we look at the block here, we have mg acting down. Well, that won't come into play in determining our natural frequency. And then we have T1, the tension in the cable here, acting up on it. And then we have this spring here, and it has a tension because it's attached to the pulley here. It has an equal and opposite tension here, T2. And its top end is fixed, and its bottom end has a displacement of x2. And we can start writing kind of some of the relationships from these figures. We might start writing equations. So this spring tells us this, because of the spring constant, we know that T1 equals Kx1. And now, because this is a rigid pulley, we know that x2, the displacement of the center, is the average of the displacements of either side of it, so that x2 is x1 plus x3 all over 2. So that's a kinematic constraint because of the rigidness of the pulley. You could also think of this as kind of a bar here, okay, a rigid bar. Now, we also know that from this spring, we have T2 equals minus 2kx2. Why is it minus? Because if we have a positive displacement, then we have a negative, we should have a negative value for T2, or a compression in the spring. And then from up here, we know that that is also equal to 2 times T1. And we know x2 in terms of x1 and x3, so we can plug that into here. And so this becomes minus k times the quantity x1 plus x3. We can take these two pieces of this equation, and we can see that the k's cancel out. The negative sign, this, we can plug this into here and take this, and so we get 2kx1 from here, and then minus k times this quantity. And so the k's cancel out. We move x1 over here, and we get that x1 equals minus x3 over 3. So this one is going to move in the opposite direction of this one, and a third of the magnitude. Now, if we look at the free body diagram of our block, we know the mass times its acceleration, which is x3 double dot, must equal T1 minus mg. So the sum of the forces acting in the vertical direction. T1 we have is kx1, and we know from this analysis here that x1 is minus 1/3 x3. So we can substitute this into here, and we get that mx3 double dot plus k over 3 x3 equals minus mg. And the natural frequency is just the square root of the equivalent stiffness, which is k over 3 divided by m. So we get square root of k over 3m. The answer in the back of the book is square root of k over 2m. And I've kind of convinced myself that that's not correct. And how I did that was I took a look at the problem where this is k1 and this is k2. Okay, so let's just make these just arbitrary values and not related to one another and see what we get. And I won't go through the complete analysis here, but I'll show you what we wind up with. If we do our analysis like we did before, we can find x1 in terms of x3. And what we get is x1 equals minus k2 x3 all over 4k1 plus k2. So if k2 were 2k1, then we would have 2 up here and 6 down here, so we get our minus 1/3 x3 back. Now, we know from before that mx3 double dot minus k1 x1 equals mg, so we can then get everything in terms of x3 by substituting in here. And so now here is our equivalent spring if k1 and k2 are independent of one another. And our natural frequency, so our natural frequency would be the square root of this value divided by m. So m, okay, that. Now, one thing we can kind of start to check with this case is that what happens when some of these spring constants go to infinity. If k1 goes to infinity, well, we can divide through by k1, and this cancels out. And so we get that this value goes to k2 over 4. So our natural frequency is the square root of k2 over 4. And does that make sense? And I'll argue that it does, because in that case, since this, what was it, k1 was infinite, and this was k1, okay, so then we just basically, this point is fixed, and so then the displacement of this point is half of that of this point. Okay, so we get twice the motion of here, and then we also get twice the force acting on this spring. So we get 2 factors of 2, and that's why we get this factor of 4 here. And when we take a square root, we get that it is the natural frequency would be square root 1/2 square root of k2 over m. Now, the other case, if we look at when k2 goes to infinity, again, we can multiply top numerator and denominator by k2. And what happens there is that we just get our spring constant is k1. We just get that left here. And now our natural frequency is square root of k1 over m. If we go back here and take a look at what that physically says, that means we have a rigid wire here that's not stretching. And so, just as we'd expect, basically this this spring gets stretched the same amount as this thing gets moved down or up. Okay, so they're basically directly coupled to one another, and so the spring constant is just k, and so that's the restoring force is just going to be k acting on this mass, and so we have a natural frequency of square root of k over m. Now, we could also look at the cases when either one of these goes to 0, but in that case we can see that the stiffness of the system would go to 0 if either of these springs' stiffness individually goes to 0, and that makes sense because if this thing were taken away, then this thing would just fall, and likewise if this thing were cut, then this would just fall too. So if either of these spring constants are 0, meaning that we cut either of these springs, then this thing is not being supported anymore.